the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. Welcome to my last video on null spaces and column spaces. In this video, we're going to talk about the kernel and range of a linear transformation, which might not sound like they're related to null space and column space, but they are. We'll first remind ourselves of a definition here of a linear transformation. A linear transformation T from a vector space V into a vector space W is a rule that assigns to each vector x in V a unique vector T of x in W such that T of Cu plus V is equal to C T of U plus T of V. By the way, that equation specifically is the linear transformation definition right there. It's linear if you can break it apart across addition and factor out constants. By the way, it shouldn't be called factoring out, but I just said that, so I'm sticking with it. And this should be true for all vectors in your vector space and all scalars in your underlying field. Now, for those who are astute, you probably have noticed there is a subtle difference between this definition of a linear transformation and the definition you were given a while back in your linear algebra course. The subtlety is with the words vector space. Those were not included before. So we're slowly defining our entire world of linear algebra in terms of vector spaces. Basically, it's that we're redefining our world of linear algebra in terms of vector spaces. So the two words up here, kernel and range, one of them we're very familiar with, the range, right? That's from functional analysis, we totally know that, but the kernel is something that a lot of people do not know. These are analogous to the null space and the column space of the matrix A. And in fact, I'm letting the cat out of the bag by saying that, but I'm going to do it here anyway. We've already discussed the fact that the column space of A is technically the range of the associated linear transformation. And we've already discussed that the null space of A is a set of vectors that gets mapped to the zero vector by your transformation. But when you're talking about linear transformations, we use yet another word or phrase to describe that set. It's called the kernel. And here it is in all its glory. The kernel of a linear transformation is a set of vectors x in the domain of T such that T of x is equal to 0. That is, it's the null space of the matrix associated with the linear transformation. Now, I should tell you that this definition holds for all linear transformations, and not all linear transformations are matrix transformations. So when you exit out of linear algebra and you go into higher level math courses and you're dealing with linear transformations there that are not based on matrix transformations, the word kernel is going to be very important because that is a set of vectors x such that T of x is going to be 0. It's a very subtle difference, one that's not going to be super important right now, but is important as you move forward. Another thing I should mention here is the kernel of a linear transformation is a subspace, and the range of a linear transformation is also a subspace because, again, kernel is the null space and range is the column space, and those are already subspaces. So just letting you know, those are going to be subspaces. A theorem that I'm not going to prove is listed here. If the linear transformation is a matrix transformation, so note this is exactly what I was just stating a moment ago, that not all linear transformations need to be matrix transformations. But if you do have a linear transformation that is a matrix transformation, then the kernel of the transformation is the null space of its standard matrix, and the range of the transformation is the column space, again, of its standard matrix. So let's go ahead and do an example. Let's define the transformation T to be the mapping from whatever this is, C01, to the same space, C01. And let's go ahead and define that. This notation means that T maps all continuous functions that are defined on the closed interval 0 to 1. So essentially you're taking all continuous functions defined on the closed interval 0 to 1. For example, y equals x, or y equals x squared, y equals the absolute value of x, y equals e to the x, y equals sine of x. All of those are continuous functions on the closed interval 0 to 1. Y equals 1 over x minus a half is not part of that because it's not a continuous function on the interval 0 to 1. It has a discontinuity at 1/2. So we have some transformation that does something to these functions and still plops them back into that space of continuous functions from 0 to 1. Who knows what it does, but it does something. Well, let's figure out what it does. This is how we're going to define it. For a function f, notice I put a little vector notation above it because I'm just considering that we're doing a transformation from a vector space to a vector space. So I'm letting my function be called a vector. So for a function vector that's continuous on the closed interval 0 to 1, we're going to let the transformation of that functional vector be the antiderivative of that function vector. Such that, now remember, antiderivatives are families of functions. For example, the antiderivative of x, if I did not clamp this down, it could become x squared over 2. It could become x squared over 2 plus 1. It could become x squared over 2 plus pi. There's an infinite number of possibilities for the output if I just said, oh, what this transformation is going to do is it's going to take our function and map it to its antiderivative. However, we're specifically going to map to the antiderivative where the antiderivative at 0 is 0. And if you take a look at all these choices I've listed here, the only one that is 0 at x equals 0 is going to be the very first one. All right, show that t is a linear transformation and describe the kernel of t. That is, describe the null space of the transform. Actually, you can't say the null space in this case because this is not a matrix transformation. Now, let me be very explicit with this because this should feel unfamiliar to you. We're going to let f and g be two continuous functions on the closed interval 0 to 1. I'm just going through and really talking about what is this transformation doing to each of those. Well, the transformation of f is going to turn it into an antiderivative, but a very special antiderivative. And that special antiderivative is the one where it turns into 0 when evaluated at 0. Likewise, we'll have a very similar definition for t of g. Now let's prove that this is a linear transformation. Again, this is not a matrix transformation, so the language I'm going to use here involves things like kernel instead of null space and range instead of column space. All right, so let's go ahead and prove the linearity of this. We want this to turn into the constant times the transformation of f, I'm going to write this over to the right, plus the transformation of g. And we require that in the end, when we plug 0 in to those vectors f and g, the output be 0. That is, we're going to go ahead and assume that t of f is capital F, t of little g is capital G, and capital F at 0 is 0, and capital G at 0 is 0. Those are our assumptions. Well, the transformation finds the antiderivative, and we happen to know, first of all, that this notation is bunk right here. Once you get outside of the transformation, it's better to rewrite those not as vectors, but as functions. And second, because we have properties of integration from our previous courses, we know that this can be broken apart to c times the integral of f of x dx plus the integral of g of x dx. But the integral of f of x dx, that's capital F. Now, when you run these integrals, you get the following: c times the antiderivative of little f plus a constant of integration I'll call capital D, plus the antiderivative of g plus a constant of integration I'll call E. Now, these constants of integration, D and E, right here, they can be glued together because they're just constants of integration. And by the way, this is a constant as well, so they kind of all glue together, and I'll write it as follows. So it's the antiderivative, capital F, plus the antiderivative, capital G, plus some constant K. However, we know the transformation of whatever function we plug in returns an antiderivative such that when you plug 0 into the antiderivative, it should become 0. To make this very clear, I'm just going to go ahead and glue together g of x and f of x. I'll call that h of x for right now. That's just the sum of g and f. For the time being, I just want to showcase something. The transformation itself requires that whatever pops out when you plug 0 in for x, the output should be 0. So let's go ahead and make that note here. Whenever you plug 0 in for x into h there, it should become 0. Now, what is h of 0? Well, h of 0 is f of 0 plus g of 0. However, we've made an assumption about f of 0 and g of 0. F of 0 is 0, g of 0 is 0. Which tells me k has to be 0 as well. Thus, and I totally forgot way back here to continue to write my c, sorry about that. I should probably have written that in, I apologize. So h is cf plus g. That's still okay, because remember, f of 0 is 0, c times 0 is 0. All right, so we get this. So the transformation of c little f plus g is actually c capital F plus capital G plus k, but we've just found out that k is 0. And remember, the important part is to note that the antiderivatives evaluated at 0 have to be 0, and they are, because again, we started with the assumption that f of 0 and capital F of 0, capital G of 0 were 0. So when you add those together, they become 0. And that shows linearity, because this is c of the transformation of little f plus the transformation of little g. And so we have shown the transformation of cf plus g is c transformation of f plus transformation of g. Thus, the transformation is linear. And sorry about that mistake partway into it. I totally forgot about that c sitting there the entire time. Now, there is a second part of this. We're supposed to describe the kernel of t. That is the set of functions, because those are our inputs, are the set of functions, right? So our transformation maps functions to functions. And we just want to know, what functions do we plug in to get an output of 0? Let me write that down more succinctly down below. So for the kernel conversation, we need to find the functions f such that the transformation of those little functions f are going to be 0 identically. That is, we want our antiderivative to be identically 0, no matter what x is. Well, if you take the derivative of both sides, you get that little f therefore has to be 0, because the derivative of 0 is 0, which implies the only vectors that we can plug in this transformation to become the 0 vector, or the 0 function, are the vectors that are always identically 0. That is, the only function that satisfies this is the 0 function, which is the trivial kernel. There you go. So this is a really abstract feeling example, but actually becomes more important as we move forward. So I do assign, if you're one of my students, I assign quite a few of these problems that involve these types of transformations where they're defined in terms of continuous functions on intervals. So please use this video as a guideline. It does help out quite a bit. All right, I think that's it. Aside from the new theorems from this subsection that we're going through, I do want to mention something here. I've added to my existence equivalence theorem and my uniqueness equivalence theorem in this table here, because, well, we've learned new material and it applies to those. So notice I've relabeled these as the existence equivalence theorem plus and the uniqueness equivalence theorem plus. And what I've added is one line at the very bottom. For the existence equivalence theorem plus, the column space of A is Rm, implies everything in this column here. That for each B in Rm, Ax equals B has a solution. For each B in Rm, B is a linear combination of the columns of A. The columns of A span Rm. A has a pivot in every row. The transformation maps Rn onto Rm. And likewise, the null space of A just being the 0 vector means that Ax equals 0 only has a trivial solution. The homogeneous equation only doesn't have a free variable. The columns are linearly independent. A has a pivot in each column, and the transformation is 1-to-1. We will continue to build onto this theorem as we move forward, but it's nice that we kind of keep it in our line of sight throughout linear algebra. All right, that's it for this video. I hope this helps you in your linear algebra course. I hope you have a great day. Be a wonderful human.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.